time horizon. Okay, so now I want to go about methods for solving Markov decision processes. So if we've got an infinite time Markov decision process, here I've just kind of stated what the answer is and you've just kind of checked it. We actually want to go through some sort of procedure to optimize the Markov decision process. Okay, so here we're going to start to cover algorithms for Markov decision processes. Okay. Okay. Just check how we're doing for time. Yeah. Okay. Good. All right. So just to recap, we've defined dynamic programs. We went through Markov chains. We put those two ideas together to come up with the Markov decision process. It's something that has this idea of randomness, like in gambling or in finance, but it also has the fact that you've got to make actions and decisions, investments, and all the rest of it. Okay. Then we moved on to consider a type of these where there isn't a finite time horizon, but you're just going to keep on playing the game indefinitely until time runs out. Okay. And we showed that the principles that we're applying in the discrete time setting, these Markov decision processes, okay, from which we derive sort of Bellman's equation, still apply in this infinite time horizon. So the Bellman's equation still applies, okay? And we proved a result that says that that works, okay? So now it's a question of how do we go about solving Bellman's equation, okay? So I'm going to kind of cover first on this side at a high level, okay? So for an infinite time Markov decision process, okay, we can't do what we did before in the discrete time case, well, not exactly, and apply induction on Bellman's equation from an initial state and get the exact solution. Okay. So we need algorithms to solve these Markov decision processes. Okay. Sometimes you're lucky enough to have an analytically closed form solution, and we'll cover quite a few of those, but a lot of the time you don't. So you just need a procedure. Okay. At a high level, if you want to solve a Markov decision process, okay, for the optimal policy, there are two steps, two main components, okay? The first of these is policy improvement, and the second is policy evaluation, okay? So what are they? So here, you take an initial policy pi, and you essentially find a new improved policy, well, so you take initial policy pi 0, should I say, and you define a new policy pi that is meant to improve the value function in some way, okay? So, for example, you might do the following. You let your new policy pi be the new maximum of the instantaneous reward, and then given I follow that policy pi 0 from thereafter, okay? So it's sort of saying, if I'm going to follow policy pi 0 from time 1 onwards, what is the first action I should choose at time 0? Okay? And that's some action that you take in order to make your policy ever so slightly better than the previous policy. Okay? The next thing is you've got your new policy, pi 0, and you need to know how good it is. Okay? And that's where policy evaluation comes in. Okay? So the idea here is you try to find out the reward function that you get from that policy. Okay, so you need to evaluate Rx of pi. Okay, and then we substitute it in again. And then we get a new policy, and we evaluate it, and we keep on going like this. Okay, so at a high level, that's what pretty much all the Markov decision process algorithms do. Okay, not everything, but you know that's pretty good high-level description. Okay. The other thing that we haven't included here is when you don't know what the transitions are and you don't know how the system's going to evolve and move. Okay, so there can also be this kind of statistical step where you need to kind of understand the randomness that's in the system and estimate the dynamics of the system as well. So that's sort of the one bit that we're missing from here. Okay, so that's where we kind of move from an area that's sometimes called control theory to an area that's called like reinforcement learning. Okay? Right. Okay. All right, so let's do one of the policy. Let's do one of the algorithms. Okay. Now, this is one called value iteration. Okay, so I'm going to do two algorithms mainly: value iteration and policy iteration. Okay. So value iteration, it provides a very important and practical scheme for approximating the solution to an infinite time horizon Markov decision process. So how does it work? You take, initially, you take all the values for all the states that you consider to be equal to 0. Okay? So you say the value, I know nothing, at times 0, so the value of everything's 0. Okay? And then, what you do is you then say, well, given the value function from the last step, what is the best action that I can take over one time step? So I take an action A from state X and I get a reward Rx of A, and then I apply beta times the expected value of the value function from the last step. So if initially V of 0 of X was 0, I'm just looking at the maximum reward I can get over one time step. Okay? So if this was the first value, first time 0, this would be equal to 0, and just take the maximum reward. Okay? So it's sort of like, what's the best thing I can do over one jump? Okay? Okay, so that's my policy improvement step. Okay? And then we need to evaluate the policy. And we just say that, well, the new value of the policy is just the argument, the maximum value of the argument that I maximized here. Okay? All right? So V of S plus 1, at the next iteration, I just take the value to be the maximum reward plus the value from the last step. Okay? So let's think about this again. Notice that really what I've done here is I've said that I'm at time 0 and I get no reward. Then, at the next time, I take the action that maximizes my reward over one time step. And then, at the next round, I'll take the best action that maximizes my reward over two time steps. Okay? And then the round after that, I'll take the best action that does the rewards over three time steps. Okay? Does that make sense to everyone? I can draw. Why don't I draw this in a picture? Let's draw a picture. So I let the values at time 0 for the states be equal to 0. Okay? So that's state, that's the first, all the states, let's say. So all these circles are all the different states that I can take. Okay? And then, at the next round, if I'm at this state X, okay, I take the action, okay, that maximizes my reward over there. So let's say I've got a reward Rx of A1 for going here, and the reward Rx of A2 for going here. I just take the one that's maximum, and then assume the value afterwards is 0. Okay? And then I look at time 2, and I could be at this state Y. Okay? What I'm going to do, I look at the reward of being in Y and taking, say, action 1, and the reward from being Y and taking action 2. Okay? And what I'll do is I'll take the best action over that one step plus the best action over the next time step. So it's sort of the best I can do over two time steps. Okay? All right? So essentially what value iteration is doing is saying, what is the optimal reward I can get over one step? Then let's find the optimal reward that I can do over two steps. Then let's find the optimal reward I can get over three steps. And let's find the optimal value function over 4 steps. Okay? and then hope that converges. Okay? Okay. Okay, and we can also define this for a minimization problem. Okay. Now, what's going to happen is if I keep doing this, these values, hopefully, are going to converge. Okay. So I just iteratively keep letting my new value, v of s plus 1, be the maximum over the next reward plus the previous value function of where I end up, and just keep iterating on and on and on. Okay? So let me just check how we're doing for time. Okay, I'll probably start on the proof of this tomorrow, but what I'll show you is a little bit what that looks like. I'll show you the example at the end. Okay, so here is a robot, okay, and it's placed on a grid. So this is exercise 21. So rather than start with all the proofs and stuff, let's have a look at this. So here, I've got a little robot, okay, and it can move left, right, up or down, okay? And with some probability, 0.8, the robot just chooses a random direction to move in amongst the available moves, okay? So with 0.2 probability, he follows what I tell him to do. With 0.8, he goes wherever he wants, just at random, okay? Now, the job of the robot is to reach one of these end positions, okay? If it reaches this end position, he loses £2, okay? If he reaches this end position, he loses £1, okay? If he reaches this end position, he gets £2, okay? So essentially he wants to get to here, all right? So what we can do is we can apply the idea of value iteration to this, okay? And I'll, let me go back. Wait, I'll do it with this one. Value iteration. Okay, so there's the example. Here's value iteration on grid example. Here's the robot. There's the rewards. Okay, and just quickly walk you through what we've done here. Okay, so I download some things to deal with numbers. All right. Then here I've defined the values of all the different points, the final values of all the different points on the grid. Okay, so these are the rewards. Okay, so there's a reward of -1 for here, a reward of -2 for this one, and this gives me the reward of +2 for this one. Okay, so that's just putting in the rewards. Okay. Then I define epsilon to be 0.8. The probability disobeys the rules, and then 0.9. I've decided to put a discount factor in here of 0.9. Okay, into the Markov decision process. Okay. Then I've defined the transitions that this Markov chain makes from going left, right, up, and down. That's just a big mess. Okay. Okay. And then here is a step that essentially does the value iteration part. Okay. So here I essentially define the new value function to be the evaluated value of going, which is best, the maximum, to go left or right or up or down, and then from those left or right or up or down. Okay? So essentially just written down as a program that maximization there. Okay? Just said, here's my old value, do a maximization over the sets of actions, and that gives me the new value. Okay? So that's what that does. Okay? And I just do that a whole bunch of times. I just update the value function 1,000 times. Okay? So we can run all of that. So, except for I need to start from here. Sorry. So let's run all of that. Okay? And it just basically plugs through the numbers 1,000 times. You can notice they're pretty stable now. Okay? And then I can print out the optimal values, okay? So it starts from a value of v equals 0, and then it'll slowly converge down to these numbers, okay? The values of all the different states, okay? And then I can just look what the maximizing values of all of those are, and that will give me a policy that says do this. Okay? So if I'm in this state, it's not worth going right because of the risk of me hitting this -2. It's worth trying to go down and around like this. Okay? So notice the algorithm comes up with some sort of forward planning. It kind of goes like, okay, if I'm here, I kind of need to plan ahead. I can't just go this way, the greedy path, straight to 2, because there's too much chance of me going to -2 here. Okay? So what it's doing is essentially sort of propagating back the values to this point and saying, actually, I need to take the longer route going all the way around to here. Okay? So that's sort of what the value iteration is doing. All right? What it'll start with is all the numbers associated with these squares being 0, 2 here, -1 here. And we'll say this is sort of the value of this point is sort of the average of that square and the squares around it. And it'll start picking up the number 2 here and its average. Okay? And this point here will pick up the average of the values of the squares around it and this -2. And it'll get more and more negative. Okay? And eventually it'll reach kind of an average value, okay, which points towards this path here. Okay? We'll say it's more costly to go here than here. Right? So you'll see that in the numbers. So it's sort of, you'll notice that the numbers that are next to the negative numbers are going to be a bit smaller than the numbers that are next to this 2, for example. Okay? All right. I'll probably upload the code on this somewhere or something like that. Who here knows how to do some Python? Does anyone know Python here? Anyone know how to program a bit? If you do know, you don't need to know how to program Python for this course. I'm not really bothered about your programming skills. But if you do know a bit, then you can have a play around or something like that with the code. Okay? All right. Okay, that's it for today. We'll talk more about this tomorrow.